Hello everyone, my name is Audier. I'm working as a data scientist at SNCF. On behalf of my team, I have the pleasure to present our work about a prognostic expert system for railway fleet maintenance. Here are the headlines of the presentation, and let's start with the introduction. 10 years ago, a new generation of communicating trains, natively fully equipped with sensors, was placed in operation in Paris, which is one of the most important mass transit networks in Europe. To realize maintenance on a large rolling fleet with operational constraints due to mass transit, a mixed maintenance solution based on real-time data analysis and condition-based maintenance has been integrated into the SNCF maintenance process. Based on prognostic expert system, this solution relies on constant signaling thresholds. These thresholds are defined using technical knowledge and physical models in order to assess the health state of a system. For more detail, you can refer to our article in WCRR 2019. The first prognostic system was based on specific data workflow to optimize dependencies between all maintenance types. However, it was designed with constant signaling thresholds, meaning that the signaling system was not always in balance with the maintenance load and does not evolve to match the maintenance need over time. To overtake these limitations, an upgrade of the existing system based on fleet statistical analysis has been designed. This presentation will focus on the upgrade of the existing expert system using fleet statistical computation to efficiently model the gradual degradation process of a system. The principal goal is to properly set the signaling thresholds to match the maintenance need over time, but also to find new relevant health indicators for complex systems where technical knowledge is too limited to create a physical model. The prognostic expert system described in this paper is based on several hypotheses. Before describing the build of such system, some definitions will be given and working hypotheses will be detailed. Definitions. A data frame is a data set of raw data sent by a train system to the wayside. Health indicators are processed data synthesized into mathematical values reflecting the health state of a system. The health state is the distance separating a system from its operating state target. To perform an efficient statistical computing, input data frames need to fulfill three requirements. Each data frame is plenty accurate to describe the functionality of a system. The amount of data is high enough, and each system is completely independent from one to another. So the numerous data frames allows a relevant computation of fleet statistics. Then we suppose that depending on several parameters listed here, the health of a system differs from one train to another. We assume that systematic maintenance is effective and reliability is suitable to consider most systems healthy. Therefore, the distribution of health state through the whole train fleet can be suitable for statistical computations. Finally, we assume that the distribution shape will also change in time because of aging effects and maintenance operations which have an impact on the health state. For example, the need of reactive maintenance is higher during the delivery and the end-of-life period. The maintenance need must be matched by the signaling system. Now it's time to detail the upgrade of the data workflow. Let's start with the preprocessing layer. All the input-output information of a system are recorded on board from the train network. A raw data frame is created from a domain of observation meshed by a sampling rate and the sensor accuracy. Data frames are gathered, packaged to raw data files and transmitted to the wayside. Each system in operation may provide logical and analogical data and contextual information. All preprocessed time series data are synthesized into mathematical values, then aggregated into indicator vectors, IV, of same dimensions, and stored in a data table with contextual information. For each IV, I refers to a specific indicator, K refers to a given system, and J refers to a timestamp. For instance, I is the rising time of a specific pantograph K computed at the datetime J. In this data table, each line matches a picture of all indicators taken at the same times, and each column matches a different indicator. This data table is reduced to a specific number of indicators, selected through an observation window. This window is used to aggregate the latest indicators or the latest filtered indicators to ensure a reliable vision on the health state over time. The size of the observation window is defined to reflect the actual health state, forgetting past events. This is based on the required time to refresh the whole observation window, the expected speed of degradation of the system, the accuracy of the data frame. For instance, an observation window of 100 indicators can be refreshed in a day in case of passenger access versus 10 days in case of a pantograph. Now let's talk about data post-processing. From the filtered IV data table, a statistical data table, STIV, is computed over time using various statistical functions. In this data table, each column refers to a different indicator, and each line gathers the results of the different indicators computed over time using a statistical function. For instance, a pantograph rising time to reach catenary can be computed with S different statistical functions over the same time window. From the previous statistical data table, it becomes possible to observe and analyze each distribution of STIV over the whole fleet. The distribution then gives us the most common value and also some systems outside the distribution. To simplify the presentation, we will consider a Gaussian distribution. In this case, sigma and mu are used to compute here health flags HF and health distance HD in order to classify a system among the fleet. Health flags are used to classify a system among three classes inside the distribution or the cumulative distribution: healthy, symptomatic, and degradation classes, corresponding to systems with normal, degraded, and unacceptable performance respectively. The health flag allows to quickly discriminate a system with degraded performance. The health distance refers to the distance between this system and the center of the STIV distribution. The health distance reports on how close a system is from a class boundary, which is convenient to discriminate systems within the same class and to manage alerts creation as a function of priority. The system workflow then is divided to process both known and unknown distributions. We use a test to define if a distribution is unimodal, and also we use shape factors like skewness or kurtosis to classify distribution. For known distribution, we will use mathematical properties to compute the health state. In case of an unknown distribution, a kernel density estimation will be used to compute the health state. Finally, all the health flags can be projected onto a plan over all the indicators to create a health map of all the system fleet. The goal of this map is to observe some cluster of healthy systems or unhealthy systems, but also to match a cluster with a specific failure signature. Now let's think about one single system in the distribution. Without maintenance operation, its health state will gradually worsen until a failure occurs. The time effect leads this system to the border of the distribution. On the contrary, maintenance operations will lead the system to the central part of the distribution in the perfect case. To be efficient, this maintenance effect needs well-designed maintenance quality and frequency. The distribution will evolve over time as a function of these two parameters, quality of maintenance and frequency of maintenance. As the sigma parameter contributes to compute health flags and health distances, If the sigma value becomes too small, we will alert on healthy systems. It's the case of the upper right of the graphic. On the contrary, a large value of sigma will lead to a system failure before any alerting. Therefore, the expert system needs two statistic thresholds based on human knowledge, the overquality threshold and also the reactive threshold, to ensure this will never happen and to keep the system under control. The whole system workflow is now synthesized on this slide, from raw data to the definition of health flag and health distance. All data are stored in database to monitor each step of computation over time. The statistical results are processed in the maintenance decision layer, which transmits alerts to the computerized maintenance management system. From this point, human is incorporated in the loop to dispatch a maintenance operation to a specific maintenance team. It's important to notice that feedback from maintenance technicians is as important as indicator computation. Human in the loop is fundamental to adjust filtering rules and static thresholds previously defined to keep our system stable and reliable. All the elements inside the red square will be discussed in a future article. Now, an example of test and filtering. It's important to notice that contextual filtering can be adjusted using the human feedback. Here, for instance, we have two pictures. On the left pictures, we have the static efforts of the pantograph, and on the right picture, you have the rising time of the pantograph. On the right picture, we can observe a second mode. The second mode observed in this case of the pantograph rising time can be suppressed using geographic filter to exclude a specific portion of a railway line where the distance between the rail and the catenary is smaller. For other cases of B modality, we can use kernel density estimation to compute the health state of the system. So, to conclude, a dynamic threshold expert system based on fleet statistics analysis was described here. Reactive maintenance alerts have already been defined for several systems. Health flags definition has shown promising results, as you can see here on this graph. On this graph, we have in green a cluster of healthy systems, and around this cluster we have several clusters of unhealthy systems. Now the game is to match one unhealthy cluster with a failure signature. This will be done in a few months, I hope. But next study will be dedicated to first analyze future results obtained by this prognostic system over a year of exploitation, but also to verify starting hypotheses and how results may impact the development of the expert system. We need also to implement the human-in-the-loop system in the whole fleet maintenance statistics system of SNCF. Thank you for your attention.